Hello, in this lecture we will take an overview of the design of an airfield and look at how its various components are and their interrelationships. Let me start with some basic background and introduction to airfield design. This has already been covered in the section on airports, but I'll just try to talk to you about the basic components of an airfield, and then we can have a look at their individual geometries. First, let us revisit the factors that govern the airfield design. These factors are the number of runways, which decide the size of the aerodrome and the area required, orientation of the runways, if they are parallel or if they are cross, then the areas will be different. Length along the runway, obviously a longer runway length means a larger land area required. The width perpendicular to the runway depending on the location of the terminal building and other areas, and the pavement type and thicknesses. There are rigid pavements and then there are flexible pavements, and both of them come with several thicknesses. And finally, the location of the terminal building could be at one end of the airport or one side of the airport or in the center of the airport with runway on either sides. All of that decides the design of the airfield. So, what are the elements of airfield design? We know that the airport system consists of two major components, the air side and the land side. In the air side, which is what we will discuss today, are the runway, the taxiway, the aprons and the gates. Of course, we will not touch upon gates a lot. On the land side area, you have the terminal building, the car parks and the rail, bus, road or metro connectivity. So, we are going to focus only on the air side, and that too looking only at runway, taxiway, apron, and also we will look at some important obstacle free zones and some surfaces. So, the interface between the two components, the air side and land side, occurs between the gates and the terminal building. Here is an image of an airport. In this airport, the runway is at the bottom left corner. The runway, as we all know, is a rectangular surface of an airport which is prepared or it is made suitable for aircraft landing and takeoff. Then we have the taxiway, and this image shows an aircraft taxiing on the taxiway. The taxiway is a defined path established for the taxiing of the aircraft from one part of the airport to the another. Primarily, the taxiway is defined as a path which is defined and established for taxiing of the aircraft from one part of the airport to the another. Generally, the taxiway is connecting the airport runway to the other components. Then we have the apron or area where the aircraft are parked, unloaded or loaded. That is also the place where they are refueled and where the passengers board the aircraft. Then we have the taxi lane, which is a part of the aircraft parking area which is used for access between taxiways and aircraft parking positions. We also have the gates, which is a section of an airport terminal for transferring passengers and airline crews to the aircraft and back. On the bottom, we see that there is a aero bridge or a jetway. This is an enclosed movable connector which extends from the airport terminal to the gate of the aircraft. So, all these, and finally we have the terminal building or the passenger terminal, which is the enclosed area to house passengers before boarding or after deboarding the aircraft. So, these are the components. Now, we are going to focus mainly on the airfield components, which essentially are the runway, the airport safety zones, the taxiway, the apron and the obstacle limitation surfaces. So, we will look at these components one by one. Let us start with the runway. Runway, as we all know, is a long piece of ground with generally a hard surface, and this has been prepared so that the aircraft can take off and land at an airport. Now, the geometry of the runway has various components which we can see. So, here is an image of the runway geometry. It has these 4 major components as listed. So, the RSP stands for the runway structural pavement. Then we have the runway shoulder. Then we have the runway blast pad at both the ends. And finally, we have the runway safety area, and also we have the runway end safety area. Let us look at each of these components in little bit more detail. The runway structural pavement or RSP is area of the runway which is designed to carry the full load of the aircraft at takeoff and landing. So, this is the structural pavement. This is where the aircraft is going to touch down while landing and also roll during the takeoff. The runway shoulder is on both edges of the runway. This is the area on the adjacent of the runway structural pavement, and this actually serves 2 purposes. It provides transition between the runway structural pavement and the adjacent surfaces, and also it supports if the aircraft is running off the pavement in case of a side wind landing. There is a tendency of the aircraft to go along the lateral direction of the runway. So, it should be able to support the aircraft, and also this is the area where we provide system for or facilities for drainage of water from the runway, so that it does not accumulate on the runway as far as possible. Then we have the runway blast pad. Blast pad is at both the ends of the runway. That is because normally when the aircraft takes off, the engines are put at full thrust, brakes are put on, and the pilot normally tests the working of the brakes and working of the aircraft for some time. So, at that time there is a huge exhaust. So, this is a surface adjacent to the ends of the runway structural pavement, and it is there to reduce the erosive effect of jet blast and propeller wash onto the runway surface, right. Then we have runway safety area or runway end safety area. Now, it is a defined surface which surrounds the runway structural pavement. Some of it is at the ends and some of it is at the sides. Together it is called as the RSA. Now, the RSA or the RESA is prepared or suitable for reducing the risk of damage to the aircraft, because while operating the aircraft might temporarily go in this area, and in the event of an undershoot or overshoot or excursion from the runway structural pavement, this area provides it safety, especially at both ends of the runway. Now, for the end of the runway, we have another very interesting option available, which is called as EMAS or the Engineered Materials Arresting System, which is an alternative to the runway end safety area at both sides of the airport. So, what is EMAS? Alternative to ASIT for terrain limitations, because sometimes you may not have enough terrain available on both sides. So, therefore, you will like to bring the aircraft to rest very quickly in a limited amount of land available. This is especially installed surface at the end of the runway. It looks like this. The yellow colored hash lines on the right hand side of the picture indicate the EMAS system. This is a, you can notice that there is a road at the end of the runway. So, therefore, so much area is not available beyond the end of this runway. So, the purpose of EMAS is to quickly stop the aircraft that moves into it. In normal operations, we do not expect the aircraft to go into this area, but in case there is a problem and in case because of various reasons the aircraft is not be able to stop on the runway, then it should go to the EMAS, and maybe it will damage the EMAS temporarily, but it will actually come to a stop, ensuring the safety of crew and passengers, right. So, it actually prevents an overrun affecting other runways, because it may get damaged, but the other part of the airport can remain operational for the other aircraft while this is repaired. Now, what was the need for EMAS? This need has come from a series of accidents that took place, noticeably this particular one, the famous accident of the SAS flight 901, which overrun on landing at the John F. Kennedy Airport in February 1984. So, an investigation of this particular accident revealed that the procedures were not followed properly. There is a requirement for the pilots to monitor and to control the airspeed of the aircraft during approach. There is a proper checklist for that, and there is a SOP which was not properly followed in this particular case. And what should have been done in hindsight is that the approach should have been missed, because the aircraft had already reached a large part of the runway before landing. So, the pilots decided to continue to land rather than to execute a missed approach, and that is why the remaining part of the runway available was too small. Okay. The pilots had over reliance on the auto throttle speed control system of the aircraft, and this particular aircraft, it had a history of recent malfunctions of this particular system. So, because of this particular incident and a few other incidents, to ensure the safety of the passengers, in this particular incident there were 192 people on board. Fortunately, no lives were lost, but around 12 people were seriously injured. So, EMACs have been installed worldwide at several airports. There is a circular by FAA in 2012 for the guidelines for installation of EMAS surfaces. It has been installed at 125 or so airports globally, and most of these airports are in the USA. But we noticed that there aren't any standards and recommended practices or SARs for EMAS from the ICAO, although ICAO does give some guidelines regarding the EMAS. In India, the tabletop airports at Mangaluru and Kozhikode, these have had accidents, and because of that there is a demand for installing EMACs at these tabletop airports, so that we do not have a repeat of those accidents. So, at a glance, here is a runway geometry. You have the end safety area, you have the pavement, and you have blast pad at both ends, and also you have the shoulder. If you take a cross section of the runway and if you zoom it, you will see that the structural pavement is not flat. It is normally having a small inclination on both sides from the center line. This is to allow water to drift away from and not accumulate at the runway. Even the shoulder also has been given a small angle in this particular section. So, there are dimensional standards for runways, the runway width, the runway shoulder, all dimensions are specified as per the FAA and the ICAO regulations. I have just taken a snapshot of the FAA regulation, but there are similar ones for ICAO also. Now, there are basically 4 types of runways based on their abilities and the functions. Okay. You can have a very simple non-instrumented runway, which is intended for operation of aircraft using only the VFR or the visual approach procedures. The second runway type is the instrumented runway, which is used for operation of aircraft using the instrument approach procedures such as the ILS system. Then we have a non-precision runway. In this, you do have some guidance, but you have visual aids and guidance with at least directional guidance for a straight in approach of the aircraft. So, you may not have the guidance of the azimuth, but at least you have a guidance for the direction. And then we have the precision approach runway, in which you have both azimuth and lateral guidance, and such a runway allows aircraft operations with a decision height and visibility constraints corresponding to the CAT 1, 2 or 3 limits as imposed by the ILS system. So, in a separate lecture on the precision approach for landing, I have talked about the ILS system, its components, and about all these various categories. So, that is all we need to know about the runway. Now, we proceed to the airport safety zones, which are actually located around the runway and in the airport, and as the name suggests, they are meant for safety. So, we have what is called as a object free area or OFA, then we have a runway protection zone or RPZ, then we have the obstacle free zone or the OFZ. These are the 3 main areas. Let us have a look at the object free area or OFA. What is meant by an object? An object could be anything that has shape, mass and size. It could be a ground structure, such as a building or any other construction. It could have be nav aids, it could be people who are moving around, it could be equipment, it could be vehicles, it could be some natural growth like a small hill, it could be some terrain, or it could be any other aircraft which are moving on the runway. All of them are objects, and the object free area is an area which is supposed to be free from all such objects while operation of the aircraft. So, centered on the runway center line or taxiway center line or the taxi lane center line, that is some area which is considered to be free of any obstacles unless they are required for a specific reason. Okay. This enhances the safety of the aircraft operations by having the area free of objects when an aircraft is operating, and entry into the OFA is not permitted in the during the operation of the aircraft, except objects, as I mentioned, which are required by function. They can be located in the OFA and they will be well lighted and well marked for the crew members to notice. They could be air navigation or ground maneuvering purposes. Okay. Then we have the runway protection zone or the RPZ. This is a area which is marked like a trapezoid at the end of the runway end. Okay. It could be at both ends, it could be at only one end. It normally has an offset of 60 meters from the end of the runway, and it has some length L and some width W1 at the beginning and W2 at the end, and these numbers W1, W2 and L, their values are given by the regulations. They are specified depending on the aircraft classification or the aerodrome classification, they are specified. The purpose of RPZ is to enhance the protection of the people and property. We had one object free area where absolutely nothing is permitted. This is also an area where we would like to ensure that we have control on what comes up there. Okay. So, in the case of an event that the aircraft lands or crashes beyond the runway end, the RPZ area is protecting the aircraft from severe damage. And then we have the runway protection zone or the, that is what it is. You can see the image of the RPZ. This part can be deleted because this slide by mistake should have been hidden. So, I think you can just cut it off in editing. Then we have the obstacle free zone or OFZ. Obstacle free zone is the airspace below 150 feet above the established airport elevation, and it is also along the runway and the extended runway center line, as you can see in this image. If you have an approach lighting system, then you have it is little bit tapered, and in the top view it becomes a trapezoidal shape. If you do not have a runway lighting system, then it will remain rectangular as shown in the right hand side. Now, this area should be clear of objects except for visual nav aids which are frangible. By frangible, what we mean is that they will be damaged and broken in case of any contact with the aircraft during takeoff or landing without harming the aircraft. So, they will be they will take the load and they will break. Okay. These obstacle free zone, it provides clearance protection for landing or takeoff from runway, and also whenever you have a missed approach. A missed approach means that you come in to land and then you decide that it is not safe to land for some reason, and therefore you just abandon the landing and climb and maybe circuit and come again or divert. That is called as a missed approach. Now, this itself, the obstacle free zone itself has many subdivisions. The first one is the runway obstacle free zone, which is the airspace above the surface centered on the runway center line. Then we have shown in the green the inner approach OFZ, which is centered on the extended runway center line, and this is only applicable for runway with approach lighting system as shown in this particular figure. And then you have the inner transitional OFZ. This is the airspace above the surfaces located on the outer edges of the runway OFZ on both sides, and these are applicable only for runway with the approach visibility of minimum 3/4 of a statute mile or 1200 meters. So, these are the subdivisions of the obstacle free zone. And if you want to have a look at the obstacle free zone from various directions, the one on the top is the top view. If you take a cross section across AA, across the runway center line, you can see that this dark line here becomes the runway, and then you have this 50:1 angle, and this area is the inner transitional object free area or object free zone, and this is also a part of that same thing. If you take a cross section along the lateral runway, you will see that this zone 150 feet above the ground, this is the inner transitional OFZ, and then you have the runway OFZ centered on the runway, and this is the runway. So, this whole area is called as the obstacle free zone. We should not have any obstacles there. Now let us move on to the next component of the airfield, which is the taxiway. Taxiway basically is a route along which the aircraft can taxi when moving to or from a runway. So, like on the left hand side, this is what the pilot sees when they are entering a taxiway, and the figure on the right shows a runway here, and in the red colored we have marked a taxiway with some small separation between the runway and the taxiway from safety point of view. This is taxiway geometry. Like a runway, the taxiway also has a shoulder on both sides with the same purpose. Then you have the taxiway pavement width. So, this pavement is like the structural pavement of the aircraft. Then for the largest or the most critical aircraft that is operating on this airport, you need to provide some edge clearance between the outermost main landing gear wheels of the aircraft and the edge of the taxiway. This is what decides the width of the taxiway. Okay. Now, there are many components of taxiway. You could have apron taxiways. These are taxiways that surround the aprons, or they may also provide a route across the aprons. You may have taxi lanes, which are abbreviated as TL. These are areas in the apron providing access to only the aircraft stands. So, here the access is only to the aircraft stands. Then you have taxiway edge safety margin, just like you have the RESA, minimum acceptable distance between the outside of the aircraft wheels and the pavement edge, as I showed you in the previous slide. This particular thing, this is the pavement edge clearance, is actually the taxiway edge margin. And then you have taxiway safety area, just like you have the runway safety area. It includes but is not limited to the taxiway shoulders, and this must be cleared and graded, drained, and it should be also free of objects, just like in the case of runway. So, you might say that a taxiway is like a baby runway or a small runway, but a taxiway is not expected to take the impact loads during landing or the loads of the aircraft when it is accelerating. It is normally expected to aircraft to be moving at low speeds or decelerating after leaving the runway. So, there has to be some wingtip clearance from the taxiway. So, the nearest object from the taxiway, there has to be some gap. This gap is also mandated by the regulatory requirements, and that comprises the object free area of the taxiway. Now, one could also look very deeply at the end of the taxiway, which has got curves. So, there the aircraft is going to take a curve. So, there has to be some minimum wheel clearance. So, you may need to build this additional extra taxiway width at the corners to allow the aircraft to taxi safely. Then there are many types of taxiways. For example, you could have exit taxiways, rapid exit taxiways, entrance taxiways, holding bays, dual taxiways, and bypass taxiways. We will see each of them one by one. In a conventional exit taxiway, you normally egress from runway for arriving aircraft, and generally the center line of this forms a 90-degree angle with the runway center line. As you can see, you have a taxiway here and you have a runway here. So, these two lines are parallel and the center line is perpendicular. Okay. Now, this can happen only at the end of the runway when the aircraft is very slow, or at the beginning of the runway when the aircraft is coming to the runway from taxiway. Okay. So, if the aircraft is going to be at a reasonable speed, it will be difficult for them to turn like this and come here. So, for that we provide what is called as a acute angle taxiway or a rapid exit taxiway. It is a taxiway whose center line forms an angle which is much less than 90 degrees with respect to the runway center line as shown in this particular figure. So, here is a taxiway and here is the runway. So, the aircraft is landing from here and it is at reasonably high speed, and instead of making it to go to the end of the runway, or instead of making it to go slow down and then turn, it is also possible for it to exit rapidly along this line, so that the runway is not occupied. So, this angle called as the intersection angle is much below 90 degrees. So, with this the aircraft can land and rapidly exit the taxiway and go to the taxiway. Then you have entrance taxiways, which provides access to takeoff at the end of the runway for departing aircraft, and also it can also act as a reverse, the final exit taxiway for the landing aircraft. Okay. So, for example, you are in this taxiway, you either come here, you can notice there is a slight additional corner strengthened for the turning aircraft, you come here slowly, go there, and then you can take off, or you may land this way and then turn this way and go to the taxiway. Then you have holding bay. Now, holding bay are areas for checks before takeoff, and we do not want the aircraft to occupy the runway, so that the throughput of the airport will reduce if every aircraft has to come to the beginning of the runway and then consume time in the warming up and run up. So, what can be done is you can create these holding bays where you can bypass the other aircraft, and if the operations of the runway are more than 30 per hour, then FAA mandates that there must be holding bays. You can notice here these are holding bays. So, this aircraft, for example, is arriving and these are already holding there and they are warming up and they will go one by one. Then you have dual or parallel taxiways, which provide a secondary taxiway segment. Now, this allows the aircraft to bypass near critical points, typically at the runway end. So, you can notice you have two taxiways here which are parallel to each other, and there is one runway here. So, aircraft can come from this runway and come this way, and there can be two aircraft taxiing. So, when this aircraft goes here and continues, this aircraft can continue this way. By the time this aircraft takes off, the other one is already coming here. Such parallel taxiways or dual taxiways are required at busy airports to have higher throughput. Then you also have a bypass taxiway, which is actually an alternative to the holding bay. Okay. Now, the bypass taxiway is always parallel to the entrance taxiway leading to the runway end. Now, if it so happens that the preceding aircraft is not ready for takeoff and blocks the taxiway entrance, then the other aircraft in the queue can use this bypass taxiway. So, here you can see this is the bypass taxiway. Okay. So, you have only one taxiway and one runway, but you do not have only one lane here, you have this bypass lane also available. Just like the runway, the FAA has got detailed requirements for the minimum distance between various artifacts and the minimum geometrical requirements. This table is taken from the FAA regulations for various airplane design groups. There are numbers here. This is just for your information. Now let us look at the next item, which is the apron. Apron is essentially an area of the airport where the aircraft are parked or unloaded, loaded, refueled, passengers board, or they are stored. So, these are the areas where you can see the aircraft standing before and after they complete their takeoff and landing respectively. So, this is also an apron where everything is parked together. Okay. Now, there are many layouts of the apron. There could be linear concepts and variations of that along a curve, or there could be pier concept or a finger concept. There could be a combination where you have the piers and you have these curvatures, plus you could have satellite concepts also, where there are aircraft parked all around one central building and then people access the building through underground means. There are many such layouts available. It all depends upon the availability of the land at the airport and the way the airport planners plan this layout. You could also have many different types of layouts. As you can see, this is a hybrid concept. There are some parked here on the pier and then there are some which go here. So, this is the apron, and finally we come to the obstacle limitation surfaces. Now, the obstacle limitation surfaces, basically called as OLS in short, they are corresponding to the airspace around the airport that is to be maintained free from obstacles. Now, this is not just the safety zone, but it is around the airport, and this is aimed to permit safe flight of operations at the airport, right. There are many of these, as you can see in this picture. Okay. So, we are going to see all of these one by one and a few more. So, as I said, the obstacle limitation surfaces are there to protect the runway from obstructions during the takeoff and missed approach. So, you can have, for example, the inner horizontal surface, you can have the conical surface, you can have the approach surface, which is on both sides in case the aircraft can be landed from both sides. You have the transitional surfaces, then you have the outer horizontal surface, and you can have the takeoff climb surface, which again can be at both the sides. Let us have a look at each of these surfaces and their geometry one by one. So, in the top view, what we have seen in the previous slide is the isometric view. Here is the same figure in the top view, and we will now see each of these in little bit more detail. Okay, and this is a cross sectional view of the surfaces. Again, we will see them one by one later on. So, let us first look at the inner horizontal surface shown as marked in the figure below. This is the horizontal plane above an airport and its neighborhood. Okay. This normally is a circle whose radius depends on the type of the runway available, and in this case it is an oval, but it can also be circular. Now, the height of this surface is 45 meters above the established airport elevation. So, the airspace which is 45 meters above the elevation of the airport, that is the one that comprises this inner horizontal surface. There is also an outer surface which we will see later. Then we have a conical surface, which is actually at the end of the outer inner surface you have this conical zone, as you can see here. This projects upward at a 5% slope, and the slope is from the periphery of the horizontal surface to the specified height above it. Okay. Now, then we have the approach surface shown in the blue color here. The approach surface, as you can see, is to protect the approach of the aircraft to the runway from obstruction. So, during the approach, there should be no obstructions from the runway, that is the blue area on both sides. It looks like a trapezoid. When you see from the top view or the plan view, you will see it will be like a trapezoid which is inclined relative to the horizontal plane. And in some cases you may have some sections in that, first, second sections of the different slopes, that also is possible. Okay. Then we have the transitional surface, the surface that is shown in the brown color in the center of the airport, but only one side is shown because it is an isometric view. Actually, it is on both sides of the runway strip. Okay. So, this lies on the either side of the runway and of the approach surface slope, and it is upwards and outwards to the height of the inner horizontal surface. As you can see in the figure in the bottom, the transitional surface is shown here, this particular area, that is the transitional surface. Okay. So, this is giving a transition from the runway to the conical area. Then we have the takeoff climb surface, which is shown in the red color at both the sides. So, this is the inclined plane to avert obstructions to the paths of the departing aircraft near the runway or even for the arriving aircraft, but mainly to do with the takeoff. Okay. Then we have the inner approach surface, which is the approach surface with the blue color on the inner side. This protects the part of the airport approach which is closest to the runway threshold. So, in this area you are the nearest, this is where the runway starts if you come land from here. So, this protects the area nearest to the runway. So, here is an idea about the inner transitional surface, which is, as you can see, it is covering above the runway. So, this is basically to control the obstacle, it is to ensure that there are no obstacles here. So, no navigational aids and other aircraft and other vehicles should be near the runway during the operations. That is ensured by defining the inner transition surface. Then there is something called as bulk landing. For that there is a surface which is a shorter inclination along the approach. So, this is the area which is prevented for walk landing. So, this is a obstacle free volume of airspace at the back end of the approach runway. Okay. But this is only defined for precision approach runways, not for conventional runways. Then if you join all these surfaces together and if you create the airspace, you can get some kind like this, which is called as an imaginary surface. These are the areas in which there are rules regarding the presence of any obstacles or any objects. Okay. As you can notice, all of them are defined purely to ensure operational safety of aircraft during takeoff and landing, and there are clear cut rules available for what objects can be present or cannot be present in these areas. So, nothing should be actually present unless required by function inside this whole volume of the imaginary surfaces. So, we will wind up now by just looking at a few important pointers. What are the common mistakes which are done by the airfield designers and planners? Failure to provide flexibility for future expansion. This is very important because no airport remains stagnant. Over a period of time, the demand increases and therefore maybe larger aircraft have to be operated. So, therefore, there has to be a requirement for expansion of the length of the runway, maybe at one end, maybe at both the ends. So, this is one very important requirement. So, therefore, the area beyond the runway at both ends preferably should not be so tight that there is no growth possible. On the opposite side, we have a situation where you overbuild the airfield in its initial phases, assuming that, oh, we will require all these things, and then you find out over time that it was an overkill, right. Then many a times there are problems in operations because of the lack of integration and coordination in planning. So, due to that there will be encroachment of items in the various surfaces, and those will create issues, those will create safety issues. So, they have to barricade those structures, you have to put signs on the airport, maybe you have to put some lighting in the night to warn the pilots about those things. And development of an airfield is a very cost intensive activity. Sometimes there is an insufficient appreciation of the economic effects of making a decision, and that can really kill the project, or it can lead to an over design of the airfield. The information that you have seen in this particular lecture has primarily come from these standard textbooks for the planning and design of airports or about airport systems. More detailed information, actual numerical numbers, various case studies and various examples are given in these textbooks, which I would urge you to read. We have just done an overview of this particular topic. This is a very detailed topic, but we thought it is enough for us to get a basic overview. Thank you for your attention.